You have probably seen this formula before. It's a formula for the sum of natural numbers from 1 through n. And n is any given natural number or integer. The formula says that if you add these numbers through n, then that can actually be computed or calculated as n times n plus 1 divided by 2. For example, 1 plus 2 plus 3 plus 4 is equal to 10. Using the formula, we have 1 plus 2 plus 3 plus 4. This is a sum of numbers from 1 through 4. We take the very last number, which is n, that's 4 times 4 plus 1 divided by 2. That's 4 times 5. 20 divided by 2 is 10. Let's test it with another sum. For example, here we go all the way to 7. Sum of 1 through 7, that gives us 3 plus 3, 6, 10, 15, 21, 28. Using the formula, we can write that sum as 7 times 7 plus 1 divided by 2. That's 7 times 8. 7 times 8 is 56. That divided by 2 is 28. Now, just because the formula works for some numbers, we cannot assume that it will also work for any number n. In fact, we could test the formula for many numbers, a million numbers, a billion numbers, but the fact is that we could never test it for all natural numbers, simply because there are infinite number of numbers. Fortunately, we have the principle of mathematical induction, a basic property of natural numbers. To illustrate the principle of mathematical induction, we use the domino principle as an analogy. Think of a line of dominoes and choose a starting domino. Now we are going to check two conditions. First, we need to check whether the starting domino falls. The second condition is whenever a domino falls after the starting domino, then the next domino in line will also fall. If these two conditions are true, then we can conclude that all of the dominoes will fall after the starting domino. Now notice that the two conditions in the domino analogy have to be verified. The first one is an action. We have to verify that the very first domino will fall. The second one is actually a conditional statement, meaning that there is no action there. If something happens, then something else will happen. For example, look at this line of dominoes. Let's pick one domino right here. If that one falls, you can see that the next one in front of it will also fall. Look at any other domino. If that falls, then the next one in front of it will fall. It's just a conditional statement. There's no action there. There's no domino falling. We simply verify that when or if this happens, then that happens. This is very important because this condition, along with the first one, pushing the first domino, will prove that all the dominoes will fall. Now, let's reflect on these two conditions. It's not enough to show that condition 1 is true. Why is that? We may be able to show that the first domino will fall, but something may prevent others from falling. This picture shows if the first domino falls, it doesn't mean that all the other ones will fall. Notice that there is a problem right there that implies that the second condition is not true. Pushing the first domino doesn't guarantee that all the other ones will also fall. It's not enough to show that the second condition is true. Why is that? The second condition is simply a conditional statement. There is no action. It simply verifies that if we pick a domino, then the next one in front of it will fall. But there is no action. No domino is falling. Now let's formally describe the principle of mathematical induction. Here we have S of n being a statement involving the integer n, and here are the two conditions. Here's the first one. It's a statement about n0. n0 is a fixed integer, and that can be related to the very first domino. We verify whether the statement about that first number is true. Here's the second condition. Pick any integer k that is greater than n0. Assume that the statement about k is true, and verify whether that can be used to show that the statement about the next integer, k plus 1, is also true. If both are true and verified, then we can conclude that the statement about the integer n is true for all integers that are greater than n0. The formal principle of mathematical induction may be a little complicated to understand, but if you remember the analogy with the domino effect, then you understand that the first condition here is an action. It's pushing the very first domino. The second condition has no action. It simply verifies a conditional statement. If both of them are satisfied, then the statement about the integer n is true for any integer or all the integers greater than n0.